Okay, so recording. Here we are, picking up where we left off last time. We had been talking about the chain rule, and we're going to talk now about how to do second derivatives with the chain rule. So, real quick, I'll point out that this is not in the book. Let me also remind you, though, that it is on the content syllabus for the course. So remember, if you go to the Course Sakai site, one of the sections is called Content Syllabus, and in addition to listing book sections, there's a fairly full column called excluded material that you're not responsible for, and then there's a relatively thin column called included material, which is stuff that's not in the book, but that is in the notes and will be covered in the lectures and that you are responsible for. This is one of those things. Okay, so what's going to turn out to be the point to it all is this observation right here, is that if you have a variable that's a function of x and y, then so are its partials. They're also functions of x and y. So this is an observation we made a while ago. If you have a function of x and y and take a partial of it, still functions of x and y, right? So that, again, is going to eventually be the point here. So let me show you how this works out just by diving into a classic standard example. So I'm going to view z as being a function of x and y here. That's represented on my diagram. And then I'm going to say r and theta are the usual polar coordinates. What I mean by that is, just like we talked about back in chapter 1, in which, if you recall, x and y were functions of r and theta. Right? R cosine theta, r sine theta, all that business. Okay, so with this setup, the question is asking us to compute this second partial. Now, the first thing I'm going to say about a second partial is exactly as you would expect. It's this being the second partial with respect to r. It's the r partial of the r partial, right? So, in order to compute then the r partial of the r partial, big surprise, I am first going to compute the r partial, right? And then I'm going to take the r partial of it. So, okay, so starting then with that first partial with respect to r. Notice we're taking a partial of z. There it is on the diagram. Partial with respect to r. There it is on the diagram. And you remember all this business that we talked about last time about paths giving rise to terms, right? And then likewise, here's another path that gives rise to a term. So I've executed the chain rule to compute the first partial with respect to r, and that part's largely over, although real quick I will point out that we have an alternative notation here for the partial of z with respect to x. Perfectly acceptable notation because z is a function of x, among other things. Okay. All right, partial of x with respect to r, that I can just straight up compute. I mean, we explicitly know what x is in terms of r and theta, r cosine theta. So the r partial is just cosine theta. Okay. And then likewise, zy, and likewise an easy partial here as well. Okay, so moving along then to, we've got this first r partial. How do I then take an r partial of that? Okay, now we do get lucky in one way. By the way, let's recopy this. Plug in what we already know about the partial of z with respect to r. Lucky break, you won't always get this lucky, by the way, but let's, get while the getting's good. Cosine theta, I claim, is a constant. Now let's think about why that's true. What is it about this that makes that a constant? The point is, I am taking a partial with respect to r. R is right there. All of the other variables in its world then are held constant. Of course, there is only one other variable, that is theta itself, constant, and if theta is constant, then cosine theta is constant. And likewise, sine theta is a constant as well. Everybody on board with that part? Yeah.
So going back to the first thing, dx/dr is cosine of theta.
Yes.
Why is dx z?
Well, because I don't know anything about this function. The way in which z is a function of x and y, all I know is that it's some function, and this isn't really a computation then, this is just a notational alternative. That's all, yeah. And I can't really crank that out because I don't know what f is. Yeah. Okay. Cool. All right. Now, having established that that's a constant and that is a constant, knowing as we do rules about derivatives of sums and all that, I can, if you will, kind of separate into two terms and factor out the constants, and that leaves us with this, which leaves our next big question of how am I going to compute to be this one? How am I going to compute the partial of zx with respect to r? Now, here's the problem. This zx here, where on my existing diagram is zx, and I don't see it there. So how can I take a derivative of something if it's not on? I don't know. What are the intermediate variables? Is z an intermediate variable? Like, is zx a function of z? How does it fit in? How does it relate to the other variables? Right? Not on my existing diagram. This, though, is where this initial big point kicks in. If z is a function of x and y, as this is, then so are its partials. So zx, being a partial of z, is a function of x and y. And I'm going to indicate like so on my updated, revised diagram. So not only is z over here a function of x and y, but zx also, and ditto zy also function of x and y. Everybody on board with that? Honestly, this is most of the trick right there. It's just to recognize what is where as you're when you find yourself looking at certain kinds of derivatives. So now let's apply the usual rules. Zx that I want to take a partial of, there it is. R that I want to take the partial with respect to, there it is. Now let's look at paths. There's a path by way of the intermediate variable x. That gives rise to what you might call the x term in that partial. And then here's another path by way of the intermediate variable y. That gives you what you might call here the y term in that partial. So all together, and again, thank you, diagram. What would we do without the diagram? It's extremely helpful. That allows me then to rewrite this mystery partial, partial of a partial. This weird thing right here, chain rule, per the diagram, boom, I get that. And don't forget, of course, that cosine theta here is a constant, multiplicative constant, just kind of come along for the ride. Right? Nothing really happened there. And we'll get to the next term in a moment. But before we get to the zy term, does everybody see what happened with the zx term here? Okay. All right. Okay, so very similar story. No surprise, I expect. For rewriting partial of zy with respect to r, we're going to get this. This constant's going to come along for the ride. And again, slowly and carefully, we're taking a partial of zy. There it is. With respect to r, there it is. Think about the various paths. There's the x path through the x intermediate variable. There's that term. And here's the y path through the y intermediate variable. There's that term. So again, just, follow the rules. I mean, my diagram tells me what are the intermediate variables, and therefore the corresponding paths, and therefore the corresponding terms. Yep.
Why does zx depend on y?
Well, I mean, just an easy example. Let's go back to when we were computing second partials the very first time. Wait, no, I went too far. Here we go. Here we had a function of x and y. I take its y partial, and check it out. The result is still a function of x and y. It's as simple as that.
Okay.
Does that make sense? I mean, it's just
because there's a y term, it depends on.
Yeah, and it's even more so than that. I mean, even had the y dependence disappeared, It's still a function of x and y. I mean, so for example, if 3x is a function of x, its derivative is a function of x because it's a function of x, and it's a boring function of x, just 3. But it's still a function of x. So likewise, this is a function of x and y, I'm going to say intuitively because you can visibly see the x's and y's, but it's not that that's essential. It truly is a function of x and y because derivatives of functions of certain variables are functions of those same variables. Okay. Yeah. No, it's a great question, but sometimes great questions have easy answers. Okay, good stuff. Let me go way forward now to where we were. Oh, gosh. Oh, here we go. Okay, good deal. Okay, it's mostly over at this point. This just kind of cleanup, really, at this point. So let's see here. What would I say about partial of zx with respect to x? I mean, there are no intermediate variables. Zx is a function of x, and I'm taking a second partial with respect to x. It's just zxx. I can't simplify that because I don't know what the function is, but this is literally a second derivative with respect to x. Again, partial of x with respect to r, I know the function x. I can explicitly write down what that is. Ditto for all the rest of these terms. And then you can take all this stuff and multiply it out and collect terms, etc., and it simplifies to that right there. Is everybody on board? There is a temptation to want to turn this into a formula. I think that's a mistake. It would be a horrifically complicated formula. I think it's much better to see it as a process that just depends on understanding that when you take partials, you create new variables, which are new functions to be inserted onto your diagram. And last little bit of advice I'm going to give about this. Don't be in a hurry when you're working second derivative chain rule problems. There's a lot going on. By the way, we got lucky in here. You may have noticed that this thing here, the partial of x with respect to r, lucky break, didn't happen to have any r's in it. That was super lucky. There's no reason why, in general, right, that you should expect the variable that you take the partial with respect to just disappear. Right? Most of the time, when you're doing something kind of along these lines, there's going to be factors of r in here as well. And so in those cases, for example, you're going to have two things here, both of which will have an r dependence. And so before you can rewrite in terms of the chain rule, you're going to have to recognize you've got a product rule situation here. And so you'd have to write out the product rule first. And then you'd have, instead of 2 terms like we did here, you'd have 4 terms. And then you'd have to take the derivatives accordingly. Yep?
Why don't we include the composition part of the chain rule when we break it down into dz, dx, and dxdr?
I didn't follow. Say it again.
So,
which part of?
Just in
up here?
One. Yeah.
Okay. Why didn't we what?
We're using the chain rule to break dz, dr into dz over dx times dx over dr.
Uh-huh.
Why do we not include the part where we compose x of r? Or
well, we do. In other words, this part of that path, how x is a function of r, that's the factor that recognizes that part of the path. That's why we have partial of x with respect to r there. Maybe I misunderstood your question?
I don't know. I think I might be misunderstanding the chain rule here. But
okay.
Previously you wrote, if you just have one function, that's the composition of f d of f of g of x, right?
Uh-huh.
And you would write that as d of...
So you're wondering about the evaluation.
Yes.
Okay, yeah. So conveniently I don't have to worry about that there because you remember I followed that up with a discussion about confusion of variables. And that if you don't confuse your variables, you don't even have to worry about that. It's kind of automatic. Right? You remember that part? So that's what's going on here. So this function is not written in terms of r and theta. if this function here had been, somehow just generically for no particular reason written in terms of r and theta, then I'd have a confusion of variables problem. But it, in some sense, couldn't have been the case because there's this automatic relationship between x and y and r and theta, and if it wasn't a function of r and theta, why in the world would I have written it in terms of r and theta? It's just really not a problem here. The notation takes care of that for us.
Okay.
Is that cool?
Yes.
Yeah. Good. Okay, so let me show you why we care about this. Why is this important? And I was disappointed to find this not in the textbook because of how much I used second derivatives with the chain rule when I was an undergraduate myself in my second major in physics. Physics has a lot of stuff like that in it, and a lot of y'all are engineers, and y'all are going to experience a lot of this as well. So, in particular, here's a great example. This is just one of many such examples. So, I'm going to tell you about something called the Laplacian operator. The Laplacian operator is denoted like this, and here's the formula for it. It's extremely important in physics and engineering if you want to understand how waves flow in 3 dimensions, which is complicated, right? Because if like as I'm talking, right, I'm making vibrations, and those waves are not just going in a straight line toward you, right? They're going in kind of spherical, they're emanating in sort of all different directions, and how do you model that? Right? If you want to understand how heat flows, again, you've seen in single variable calculus classes extremely oversimplified cases of there is a hot location and a cold location, and there are only 2 locations, and heat flows from the one location to the other location. It's a terribly oversimplified story. In reality, heat is distributed throughout 3 dimensions, and it kind of flows in all different directions. Also very complicated. And then things about potential energy of when you have charged particles arranged in a certain way, and electric potential, this kind of thing. All of these, understanding them requires understanding the Laplacian. So this is a huge deal in physics. Now exactly how the Laplacian fits in with all of this physics, that's a topic for an engineering or physics class, right? I'm not going to spend time on that. But here's the thing. Rather than writing in rectangular coordinates, I claim that you can also write the Laplacian. This is the exact same Laplacian. You can write it in spherical coordinates. And so you get this monstrosity here, which does not look like an attractive alternative. Right? Given your choices, right? Which of these would you rather deal with? I'm pretty sure most of us are going to probably, for lack of reasons otherwise, pick the shorter one, right? It looks easier. But this is a mistake. Turns out the spherical Laplacian is extremely valuable. Now, before I show you how valuable it is, let me show you where it comes from. It comes from applying the chain rule and taking second derivatives in this diagram right here. Notice, in comparison to the previous page, we have a function of position, a function of rectangular variables, with the understanding that those rectangular variables are functions of different coordinate system variables, in this case spherical instead of polar. Right, so this is highly analogous to the previous page, and I can start computing. For example, I can compute the partial of f with respect to rho. There's f, there's rho, chain rule. And with that computed, I can multiply by rho squared, and I can then take the rho partial of all of that. Again, let the diagram be your guide. Use the chain rule where necessary. Blah, blah, blah. Here I have a second partial with respect to theta. Well, again, there's f, there's theta. Second partial, again, intermediate variables, just like on the previous page. And if you crank all that out and plug in for them, this expression, this great big thing, when you plug in for it, will turn exactly into that. Okay, so that's where this monstrosity comes from. Now, why is this monstrosity useful? Isn't it clearly uglier looking? No. Let's look at this real world scenario. Engineering real world scenario. If you want to understand electric potential, you have an arrangement of charged particles, and you want to know what's the voltage in space as a function of location as a result of charged particles being whatever they are. Well, the equation that you need to solve, the equation that needs to be satisfied is this right here. The Laplacian of your voltage function, your potential function, has to equal to 0. Okay, now I claim, and we're gonna work this out for ourselves here. I claim that this function right here is an answer. This satisfies that equation right there. And so again, you can think of this two different ways. You can think of this in spherical coordinates, roughly 1 over rho. Or you can write that in rectangular coordinates, which is not that much worse. It's got a square root in the denominator, so not really super happy about that. And, well, there are 3 different variables involved, and okay, all right, that's a little bit more annoying, but it doesn't look that bad, right? So that said, here's our options. I can do my Laplacian in rectangular or spherical coordinates. Take your pick. Having made that choice, I can write my candidate function f in either correspondingly rectangular or spherical coordinates. And so in order to check this equation, in order to compute what I have on the left here, I can either compute this or I can compute this. And again, as it stands, at a glance, most people are going to go with option 1 here. Right? Again, mistake. This is a pretty brutal calculation up here. Everyone should do it once in their lives. It's kind of tedious. It's annoying because you've got fractions and exponents that are fractions. And it's tedious. It's going to take you a full page of annoying calculus to crank this out. But again, everyone should do that once in their lives. I did mine. It's your turn. I encourage everybody to crank that out. Just so you can say you did. Everyone should be able to say they did. Let's do this one down here, though. I claim we can do this at a glance. This one's easy. Dare I say super easy. Here we go. Let's look at this first term in the spherical Laplacian. The very first thing that I've got to do with that first term is apparently I'm going to be taking the rho partial of 1 over rho. Constants don't matter. So that gives me negative 1 over rho squared. Let me get rid of the rest of this junk. I get negative 1 over rho squared. When I multiply that by rho squared, I get just a constant. And then when I take a derivative of any description of that constant, I get 0. So this term here, at a glance, I didn't even have to write anything down. At a glance, that term is 0. Next, let's look at this term. I'm going to need to take the phi partial of an expression that doesn't have any phis in it. 0. Boom. Gone. That whole term is 0. And then lastly, you can probably see this one coming here. Very first thing I'm going to need to do is take a theta partial of an expression that doesn't have any thetas in it. 0. And game over. We're already done with the spherical coordinates calculation. And the equation up here is satisfied. So in spherical coordinates, it just works out nicer. Even though the Laplacian itself is kind of a monster, much easier to do business in spherical coordinates than in rectangular coordinates. Yeah. No. Don't. Yeah, no need. Yeah. Too much to remember there. I've never memorized it either. Yeah. Okay. Now, real quick, I mean, just, did we get lucky here? Or fundamentally, why is it that the spherical Laplacian, despite seeming appearances, how did it work out so nicely? And the answer is, roughly speaking, if you think about what's going on here, if you have a single charged particle and it's creating potential, electric potential, or mass with gravitational potential, whatever, those are dependent on distance. Distance is rho. The function itself is intrinsically natural in spherical coordinates. It just makes sense. It's a spherical looking thing. shouldn't be a surprise that it goes down easy in spherical coordinates. By contrast, you try to do it in rectangular coordinates, and it's a pretty unnatural coordinate system, really, right? X's and Y's and Z's. Why are we keeping track of that way, this way, and that way when we're intrinsically talking about a radial distance as being the fundamental object of interest? So it's not really that surprising in retrospect. Okay, so in your not-so-distant futures in engineering classes, when you find yourself looking at the Laplacian and they say, hey, apply the Laplacian to this function, if they don't insist that you do rectangular coordinates, right, go ahead and look up my old notes here and find the spherical Laplacian and do it this way and save yourself a ton of trouble. Everybody happy? Alrighty. Okay, next thing, section 2.6. We're going to talk about something called directional derivatives. I'm going to sort of work my way up to it, though. I want to start off by reminding you some things that we know about partial derivatives. This is old news. It's the slope of a graph. And, details as you're moving in a certain direction. Of course, there's a bunch of different cross sections, etc. It's a multiplicative factor. Recall, this is one of my favorite points of view about derivatives. Derivatives relate input changes and output changes, and the way that a partial derivative does that is it's a factor that you multiply by input change to get output change. Now, something that we haven't really talked about before, I claim that this formula here is an alternative way to think about how to compute a partial derivative. And notice what I've got here. We're starting at some point A. And this extra term over here, TE1, when you add that in, notice there's a bunch of zeros in this, which means that altogether A plus T times this vector, most of the coordinates don't change. Most of the coordinates don't have any T's in them at all, because EI is mostly zeros. Right? Then there's just one coordinate, the ith coordinate. The only one where anything happens, and there's just a single term T there. So what that does then, this part right here is effectively equivalent to the part where we let all the variables be constants except for one. Right? That's sort of, the first part of the definition of a partial derivative. It comes from this part of this equation. And then, second part of the definition of a partial derivative, just take the derivative with respect to that one variable. And keep in mind, this t is now sitting in just that one position. So d by dt is the taking the derivative with respect to that one variable. So if you'd like, you can crank this out with the chain rule, and what you will find is it is exactly what I claim. It is exactly that partial derivative. That's a little bit of algebra, but intuitively speaking, I think I hope that's at least a little bit satisfying. Okay. All right, so we've got this point of view on partial derivatives, and then here's another one we haven't really quite talked about. This is another one that you can argue by way of the chain rule, but also it's super easy if you just punch this out. Right, the gradient is a vector that has all the partials in it. Dotting with EI means I'm going to multiply most of those coordinates by 0. And I'm just going to have 1 times the ith entry, namely I'm going to have the ith partial. Right, so just crank out this dot product and out comes a partial. Okay, so all together then, partial derivatives are these 4 things. Is that cool? All right, now I want to call your attention to a certain aspect of how I've written this. Notice nowhere in how this is written on the screen does it say anything about coordinates. Right, now certainly when we talked about partial derivatives the first time, I said let's think about most of the coordinates are going to be a constant and blah blah. Take the derivative with respect to this coordinate, and it was a very coordinate heavy discussion. But that's all optional. That viewing functions of that apply in space in terms of coordinates is a convenience. But it's really not necessary. For example, in this room right here, we could talk about the temperature function. And I could say that's X, that's Y, that's Z, and let's have temperature be a function of X, Y, Z. But I don't have to. I can just say, look, temperature is a function of, it depends on where you are. You pick a point, let's say right here. At that point, there's a temperature. I don't need the coordinates. I just need a thermometer. And I can measure the temperature anywhere in this room, coordinate-free. Does that make sense? So I want to encourage y'all to, sometimes, and this is a great example of it, step away from coordinates. Step away from the idea of, using the convenience of coordinates to compute things, and think more in sort of the abstract of, what is it that's really happening? And understanding things in terms of points and vectors, independent of coordinates, is ultimately more natural. Okay, so with that in mind, looking at all of this stuff, what is it about the fact that I'm moving parallel to an axis that makes this all come together? Rhetorical question, and the answer is not a thing. There's nothing in anything that's on the page that makes any reference, particularly to in this direction that we're going. It's very important that it be in the direction of an axis. Not at all. Right? And if you're thinking about a function coordinate free, you kind of wouldn't expect there to be what do the axes have to do with anything? Right? If you're not viewing things in terms of coordinates, which you don't have to, axes don't matter. So what I'm going to say next is not a proof, and it's not a rigorous argument, but I think I hope it'll be intuitively satisfying, and I'm going to prefer to use the intuition as opposed to the rigor. But this ought to be true. Let me say this more carefully. The fact that this slope and this factor and this expression, the fact that these are all the same, should be true no matter what direction I'm looking. So that's the intuition behind the definition I'm about to make here. We're going to define a directional derivative. If you have any unit vector, v, I don't really care what direction it points. Shouldn't matter anyway. Any unit vector, I can define this expression, I can define this expression, I can talk about what the slope of the graph is in that direction, and I can talk about what the multiplicative factor should be in that direction. And just like with partial derivatives, all of these things are equal. It's just a kind of a rip-off of what we talked about up here. Again, I'm not doing this rigorously, it's not my goal. But basically, these are partial derivatives, just not along an axis. It's just a partial derivative kind of at an angle. All the same formulas, all the same interpretations. And so this is a new object of interest. We're going to call this a directional derivative. This is the notation that we use for it. Notice that the vector that defines which direction we're looking is part of that notation. It's also part of the terminology there. Right? But whatever unit vector you have describing a direction that you could be moving, all of these things are just as equal here as if you were moving parallel to an axis. So that's the big idea. It's called a directional derivative. Let's see here. Let me show you an example how to use this. Oh, I'm sorry. I'm getting ahead of myself. Let me draw you some pictures. What do we mean by slope of the graph in the v direction? So recall, when you're taking a partial derivative, you're going either in the x direction or in the y direction. Those are partial derivatives. Again, coordinate free, That's just an arbitrary pair of directions. There's nothing magic about them. There's no reason why they're better than any other directions. And along those lines, no pun intended, in this direction, v being a unit vector, I can talk about this plane, this vertical plane. I can take a cross section in that plane. That gives me a curve like this. I can talk about the tangent line to that cross section. Right, and I can talk about the slope of that tangent line to that cross section of that graph. And the directional derivative gives you that slope. Just like a partial derivative does. Is that cool? Everybody okay? Okay. All right. Now let's talk about the multiplicative factor business. It's what you multiply by, I'm going to call it input change. Either how far did you move in the input direction, or at what rate are you moving in that direction? What you multiply by that to get output change correspondingly, how much the function changes, or what's the rate that the function is changing. The thing you multiply by the input change to get that output change is a directional derivative. And if you look at how I've got it written here, notice, doesn't it make sense that this thing that I multiply by the green to get the blue just looking at the notation, doesn't it really feel like that ought to be called DFDS? Everything kind of fits, it just looks like it ought to work right. So this is another interpretation of directional derivatives. We interpret directional derivatives as being DFDS. It's how fast is the function changing, not per unit time. Right? By the way, I don't even know if I'm at this point and entertaining moving in this direction. I haven't even decided that I am moving in that direction yet. I'm just entertaining, hey, hypothetically, if I were to move in that direction. I don't have any actual speed. And I can still talk, though, about per unit distance that I might move in that direction. How much does the function change? So like, for example, here in this room, again, we've got temperature in this room. I'm currently here. It's a certain temperature here. I could move over there. As I go in that direction, for each foot that I move in that direction, maybe let's go a little bit more off angle. For each foot that I go in that direction, how much does the temperature increase? Change in the function per unit distance, not per unit time. Okay, examples. Let's see here. I want to compute, I've got a function here. I want to compute the slope of the graph of that function in a certain direction. Fine. Okay, well, slope of the graph, directional derivative. Right, this is one of our primary interpretations of directional derivative, slope of the graph. So, I'm going to need to compute this directional derivative. Per the previous page, directional derivative is computed with this dot product right here. Right, directional derivative computed with that dot product. How handy. Gradients are easy to compute. Dot products are easy to compute. Is that cool? Okay, so let's see here. Now it's plug and chug pretty much. Well, a couple little twists. But first thing, I got to compute the gradient given a function. I can compute the gradient. It's made up of a bunch of partials. I do have to plug in the point where I'm at. I'm at the point, 3, 1. So x is equal to 3, y is equal to 1. You plug that in, our gradient becomes 6, 2. Now let's talk about the what is my vector. It says here I want to go in the direction of this vector. The problem is this vector is not a unit vector. This vector, clearly not a unit vector, but notice the requirement. if you're going to use any of these ideas, if you want to use the term directional derivative, it's got to be a unit vector. That is important. Okay, so I need a unit vector that points in the relevant direction. How am I going to find a unit vector that, color codes, let's see, a unit vector that points in the relevant direction? Well, unit vectors are just non-unit vectors divided by their own magnitudes. So I'm going to take the given vector, divide it by its own magnitude, which conveniently is 5. My unit vector then, the thing that's going to allow me to do the directional derivative is that thing right there. And then arithmetic, and we win. Is everybody happy? Okay, one heads up I want to give you. There's an easy mistake to make that this question demonstrates. Notice we started at a given point. Let's say that point is there, whatever. And where it says go in the direction of, so some direction, and the direction is given by this vector, 3, 4. So there's that vector. That's the direction we're supposed to be going. Don't forget, vectors have 2 geometric features. They have a magnitude and they have a direction. And the phrasing of this question means, of the magnitude and the direction, consider the direction that this vector is pointing. That's the direction I want to go. Okay. Here's the misinterpretation that a lot of students can make. And I just want you to know where the landmines are so you don't step on them. Some students will interpret this as being a point. And 3, 4 as a point. Now keep in mind, we're not at the origin. This blue location, that's not the origin. 3, 4 as a point might be like over here. In fact, come to think of it, it's directly above 3, 1. Right? So it's like right there. As a point, that's where 3, 4 is. And in the direction of, one could perhaps, loosely, sloppily, think that means, you're going toward that point. And so some students might just go in completely the wrong direction. Everybody see the distinction between the direction that a vector is pointing and the direction toward the point that this vector corresponds to, but that we're not actually interested in. So anyway, you want to make sure you don't misinterpret and do the wrong thing here. Okay. On an exam, if you're not sure which of these I mean, come up and ask. Right? I'll be happy to clarify what the intention was of the phrasing. But in this case, I think it's pretty clear here in the sense that it does say vector 3, 4. And by indicating vector 3, 4, I think it's pretty unambiguous that that's saying don't interpret this as a point. Okay. All right, another example. This next example is morally equivalent. The big difference is that what the question is asking, it says compute the derivative with respect to s, which is, I remind you, one of our interpretations of directional derivative. So again, the question, just directly from the phrasing, we want to compute directional derivative. And then again, a lot of the stuff is the same. Directional derivatives are computed with this dot product. In order to compute that dot product, we're going to need the gradient. Let's see, I'm going to have to take this function here. I'm going to have to take its gradient, plug in the point in question. Don't forget, we're interested in what's happening at a given particular point, A. And the gradient then... went too fast. The gradient turns into that. Again, be careful about the vector. It does need to be a unit vector. Being a unit vector, you've got to take whatever convenient vector happened to be pointing in the direction that you want, and you've got to divide it by its own magnitude to get the unit vector. pointing in that direction. And then dot product answer victory. All right? Okay, that's the big idea. So now I have to give you an apology. It's not my fault. I didn't do it. But nevertheless, I'm going to warn you about a dangerous thing, and that is in some contexts, not in this course, but in some outside of Math 219, the rule about it has to be unit vector is removed. In some contexts, heads up, they will define directional derivative as follows. They will just scratch out the word unit and say, oh yeah, any vector v, whatever your vector v is, fine. You can use that vector. You put it in all the same places, and then they use the term directional derivative, etc. So what gives? Why would they do this? And here's the reason why. When you do this expression, I should color code this better. This expression here is still pretty natural. This still says I'm at a point A, I'm moving with some velocity. Now here, this is not just representing a direction. Here, this actually represents an actual velocity. I know not only what way I'm going, I know how fast I'm going in that direction too. And again, very real world. Sometimes I do know both where I am and what velocity I'm moving at. And in such a case, this tells you how fast your output function's changing. Very natural thing to want to know. And here's the even better news. Not only does this expression still make sense, it's still computed with this formula just the same. So this is still a really useful situation, right? That this is still a useful object. It's computed by a convenient formula. Directional derivative kind of gets at, as terminology, what it is that's happening here. Still pretty interesting. The only cost is it's no longer a slope, and it's no longer a factor. So all of this business down here you lose. So it's like this. It's like when you do things this other way, when you remove this unit vector requirement, the term directional derivative applies more broadly. That's a good thing. That's nice. It applies more broadly. You don't get to know as much about it, right? You don't have these interpretations. But it does apply more broadly. So it's a pro-con thing, right? It's really not clear which of these is a better choice. Now, all of that said, in Math 219, which is your immediate concern, right? In Math 219, unit vectors only. That's the book's convention, and I'm going to therefore make it the course's convention as well. In this course, the term directional derivative means that the vector in question must be a unit vector. The only reason I'm telling you about this alternative way of doing things is that when you get out of Math 219 and you're in future engineering classes, physics classes, whatever, I don't know what convention they're going to have. Right? They might choose to do it the other way. So you have to always be heads up about this. Right? Outside of Math 219, somebody says directional derivative. Oh gosh, what kind of person is this? Is this a unit vector kind of person or not unit vector kind of person? And then interpret accordingly. So, like I say, word of warning, heads up, and my apologies. Okay. All right. So, oh golly, we have 1 minute left. Okay. Let me set a stage. Next question we're going to consider is supposing that we're at a particular point in the domain of some multivariable function, and I've got some multivariable function. I like to think of temperature here, and let's suppose that as I sit at this point A, let's suppose I'm cold. and I want to warm up, and I want to know which direction should I start moving. Let's not worry about how fast I'm going to move. Obviously, I'm going to move as fast as I can. But in which direction should I move so that the rate of change of the function is as big as possible, right? I don't want to go off in some direction like this if that's only going to have temperature increase at a relatively slow rate. I want to know which direction should I move to make my temperature increase as fast as it can. So, reasonable question, how do I maximize this directional derivative by choosing among all possible unit vector directions? And we'll talk next time about how to maximize that and how to find that best possible direction. Y'all have a good Monday. See you on Wednesday.